You think we're close. Admit it. Somewhere in the back of your mind, you've got a little folder labeled Probably Aliens, and every few months a headline gets filed into it, a gas in some atmosphere 80 light years away, a paper somebody's already calling a biosignature before the ink is dry. And I'm here tonight to tell you something that's going to annoy some of you and relieve others of you. We are not closer to detecting alien life than we were 10 years ago. We are closer to detecting things we don't yet know how to explain. Those are not the same statement, and the distance between them is the entire subject of tonight. I want you to sit with that, because it's not a rhetorical trick, it's the whole ball game. Every single time in the history of this search, every time we have mistaken our own ignorance for evidence of biology, and then spent years walking it back, not because scientists are fools, because the universe is very good at producing things that look alive without being alive, and we are very bad as a species at sitting in the discomfort of I don't know yet. We want the answer to be yes, and wanting the answer to be yes is the most dangerous instrument in the entire toolkit of science. So tonight, I'm not going to tell you whether we found aliens. I'm going to show you exactly how you would know if we had brick by brick how this actually works. So the next time you see a headline, you're not at the mercy of a press release. You'll be able to take the claim apart with your bare hands and see what's actually holding it together. Let's start from the ground. What does it even mean to detect life on a planet you will never visit, around a star you will never see except as a point of light? You can't send a probe. At our fastest spacecraft speeds, a trip to even the nearest exoplanets would take tens of thousands of years. So whatever we're going to learn from light photons that left a planet's atmosphere, crossed the void for years or centuries, and landed in a telescope mirror here on Earth, carrying with them, if we're skilled enough to read it, a fingerprint of what that atmosphere is made of. Here's the first thing most people don't appreciate. Starlight is an encyclopedia. When white light passes through a gas, the atoms and molecules in it absorb very specific wavelengths, and only those wavelengths, because electrons can only jump between fixed energy levels, not in between. So when starlight filters through a planet's atmosphere and you break it into a spectrum, you don't get a smooth rainbow. You get a rainbow with thin, dark lines cut into it, like a barcode, and each line corresponds to a specific molecule. Water has its signature, carbon dioxide has its own. Methane, oxygen, ozone, each their own. This isn't guesswork, it's physics going back to Kirchhoff and Bunsen in the 1850s, and to Fraunhofer before them, noticing dark lines in the sun's spectrum nobody yet understood. The exoplanet hunters didn't invent this idea. They inherited it, and then had to solve an engineering problem absurd enough to make Fraunhofer laugh. How do you read a barcode 1,000 times fainter than the glare of the star sitting right next to it? Now, here's where it gets strange. Picture trying to see a firefly sitting on the rim of a searchlight from a mile away in the rain. That's the contrast problem. A star like the sun outshines an Earth-sized planet by a factor of roughly 10 billion in visible light. The way around this, one of the most elegant tricks in practical astronomy is to wait for the planet to transit in front of its star and measure the change in light. During transit, a sliver of starlight grazes the planet's edge and passes through its atmosphere on the way to us, picking up the chemical barcode. Subtract the spectrum of the star alone from the spectrum of star plus atmosphere, and what's left over, in principle, is the signature of the air on another world. That's transmission spectroscopy, the workhorse technique behind nearly every atmospheric detection you've heard about from the James Webb Space Telescope. I want to tell you something I got wrong, because public intellectuals owe you their mistakes, not just their victories. Early on, when transit results started coming out of Hubble, I was, like a lot of people in this field, too quick to trust flat, noisy spectra as meaningful non-detections. We'd see a featureless spectrum, and the interpretation was cloud-free atmosphere, no expected molecule. In a number of cases, what was actually happening was that high-altitude haze was blanketing the lower atmosphere and flattening the spectrum, hiding signatures that were there all along, just inaccessible to the grazing starlight. The absence of a line is not the absence of a molecule. It might just be the absence of light reaching that molecule. That distinction sounds pedantic until entire conclusions hinge on getting it backward. So say, with better instruments, you do get a real signature. Water vapor, carbon dioxide, maybe methane. Is that life? No. And I need you to feel the weight of that no. These are some of the most common molecules in the universe. Full stop. They show up in interstellar gas clouds with no planet anywhere nearby. They show up on lifeless moons. Titan, a moon of Saturn, has lakes of liquid methane and an atmosphere thick with organic haze. And as far as every probe we've sent there has found, it is not teeming with biology. It's running a purely chemical playbook. Photochemistry, breaking apart methane and nitrogen high in the atmosphere, the fragments raining down as orange sludge for billions of years. The Cassini-Huygens mission found rivers, lakes, even shorelines there, an entire alien hydrological cycle running on hydrocarbons instead of water. That's beautiful chemistry, and it has nothing to do with anything being alive. Organic does not mean biological. Organic chemistry just means carbon-based chemistry, and the universe does enormous amounts of it with no help from anything alive. This is the central discipline of the whole field, and it's the part that never makes the headline. A biosignature is not a single molecule. It's a molecule, or a combination of molecules, in a context, at an abundance, that's very hard to produce any other way. Let me give you the cleanest demonstration of this, and it requires looking at the planet you're already standing on. Earth's atmosphere is about 21% molecular oxygen. If you didn't know anything about biology and were doing atmospheric chemistry from first principles, that number should bother you, because oxygen is one of the most chemically reactive substances there is. It wants to react rusting rocks, burning carbon. It does not want to sit around unreacted in an atmosphere for long. Left alone, geological and chemical processes would scrub it down to negligible levels within a few million years, a blink geologically. The only reason Earth's atmosphere has stayed 1/5 oxygen for hundreds of millions of years is that something is continuously replenishing it faster than chemistry removes it. Photosynthesis. Cyanobacteria, algae, plants, an entire biosphere pumping out oxygen day after day for an almost incomprehensible span of geological time. The oxygen itself isn't the signature. The fact that there's so much of it sustained against the relentless chemical tendency for it to disappear, that's the signature. It's not a molecule, it's a disequilibrium. Evidence that something is actively fighting entropy's pull toward a boring, reacted, settled down atmosphere. And on Earth, the thing doing the fighting is life. Now you understand why exoplanet scientists get cautious, almost defensive, when oxygen comes up in a press conference, because you can build a planet with substantial atmospheric oxygen and zero biology. Intense ultraviolet radiation from red dwarf stars, which make up the majority of stars in our galaxy, can split water vapor and carbon dioxide apart through a process called photolysis. And if the planet then loses its lighter hydrogen to space, hydrogen being light enough to escape a planet's gravity over geological time, in a way oxygen is not. You're left with an oxygen-rich atmosphere built entirely by photochemistry, no biology required, no photosynthesis required, nothing alive anywhere in the picture. This is not a hypothetical worry invented to ruin your fun. It's a documented, modeled, taken extremely seriously false positive pathway, And any serious biosignature claim has to address it directly by checking what else is in that atmosphere alongside the oxygen, because the chemistry leaves other fingerprints. Carbon monoxide abundance, for instance, behaves differently depending on whether you got there by photochemistry or biology. This brings me to the case half of you came here for, and I'm not going to dodge it, because dodging it would be cowardly, and you didn't come here for cowardly. K218b, a sub-Neptune-sized planet, roughly 120 light-years away, orbiting a red dwarf, sitting in its star's habitable zone, meaning the zone where, if conditions were Earth-like, liquid water could exist on a surface. In 2023, JWST observations reported detections of methane and carbon dioxide, and notably did not see strong ammonia signatures, leading some researchers to propose a particular model, a Haitian planet, a word built from hydrogen and ocean, meaning a thick hydrogen atmosphere sitting above a liquid water ocean, potentially habitable in a way utterly unlike Earth. Then in 2025, the same team reported something that detonated across every science section on the planet, a possible signature of dimethyl sulfide, a molecule that here on Earth is produced overwhelmingly by marine biology, specifically phytoplankton. Headlines ran with strongest evidence yet of alien life. Here's what actually happened in the scientific community. And it's a far better story than the headline, because it's a story about science actually working the way it's supposed to. Within weeks, other research groups went back through the same data and pushed back hard. Some found the statistical significance of the dimethyl sulfide detection much weaker than initially reported, hovering well below the threshold the field itself uses to call something a confident detection. Others showed you could fit the same spectral data reasonably well with entirely different molecules, some carrying no biological implication whatsoever. Still others questioned the Haitian model itself, suggesting K218b might not have a water ocean at all and might instead be a scaled-down gas giant with a deep, hot, high-pressure hydrogen envelope and no habitable ocean surface anywhere, a place where the signal could come from atmospheric chemistry with no life required at any stage. Notice what just happened, because it's the whole lesson of tonight compressed into one real current dispute. Nobody is lying. Nobody is covering anything up. The original team published their data and methods openly, exactly as they should, and the response from the rest of the field was not shut up. It was show me. And then a half dozen groups actually went and checked using the same public data and found legitimate grounds for disagreement on multiple levels: the statistics, the chemistry, the underlying planetary model itself. As I'm speaking to you tonight, that argument is not resolved. K218b might turn out to be the first hint of an ocean world with biological activity in its atmosphere. It might turn out to be a hot, oceanless world where weird photochemistry mimics a few spectral features of a biological molecule. I genuinely do not know which, and neither does anyone else yet, and I would not trust anybody standing up here telling you with confidence that they do. We have done this before. We have been here before, and I lived through one of the versions of it, close enough to feel the heat. In 1996, NASA scientists studying a meteorite called ALH 84001 blasted off the surface of Mars by an ancient impact and eventually landed in Antarctica, announced they'd found possible evidence of fossilized microbial life structures resembling tiny bacteria, certain mineral patterns, organic compounds called polycyclic aromatic hydrocarbons. President Clinton gave remarks about it from the White House lawn. For about a news cycle, it was the biggest science story on Earth. And then, over the following years, the scientific community went to work the way it's supposed to and one by one, the lines of evidence were challenged. The fossil structures turned out to be far smaller than any known living cell and consistent with purely mineral crystal growth. The organic compounds were shown to be plausibly explainable as contamination from Antarctic ice or as products of non-biological chemistry. The magnetite crystal patterns, initially compared to patterns produced by certain bacteria on Earth, were shown to also form through inorganic processes under the right conditions. The case fell apart, piece by piece, not because anyone behaved badly, but because that's what rigorous follow-up is built to do to a weak claim, and a weak claim is exactly what it turned out to be. To this day, there's no scientific consensus that ALH 84001 shows evidence of life. I bring this up not to mock the 1,996 team. I want to be clear about that, because there's a cheap version of this story where the lesson is scientists got it wrong. Haha. That's not the lesson. The lesson is that the system worked. A bold claim was made on real data, in good faith, and then tested to destruction by a community that cared more about being right than about being first. That is what's supposed to happen to every single biosignature claim from now until we actually get one that survives the gauntlet. The day will come, I believe, that when a claim goes through this exact process, published, attacked from every angle, reobserved, reanalyzed, checked against every abiotic alternative anyone can dream up and survives. That will be the day. Not the day of the first press release. The day, possibly years later, when nobody serious can find a hole in it anymore. Here's something that should genuinely unsettle you, and I don't offer it as comfort. We don't know what the complete list of false positives looks like. We're not testing candidates against a finished catalog of every non-biological way nature can produce a pattern. We're testing them against the catalog we've currently thought of, and that list keeps growing. New photochemical pathways, new ways stellar radiation interacts with atmospheric composition that nobody had modeled before, which means any claim today carries an uncertainty that doesn't show up cleanly in anyone's error bars. Not just did we measure this correctly, but have we even thought of every way to be wrong yet? I had a real argument about this once, years ago, with a colleague, and I'll spare you the play-by-play of who said exactly what, but the substance stuck with me permanently. The argument was about whether we hold biosignature claims to such a brutally high standard that we risk dismissing a real discovery just to avoid the embarrassment of a false one. My colleague's position, roughly, was that science has an asymmetry problem. A false positive that gets walked back is embarrassing but survivable, while excessive caution that causes us to sit on a real signal for an extra decade, second-guessing it into the ground, has a real cost too, a cost in time, in funding, in the next generation of scientists who might lose interest in a field that seems perpetually unable to commit to an answer. I didn't fully agree with him then, and I'm not sure I fully agree with him now, but he was right about one thing that changed how I talk about this in public. Caution is not free. It feels free because it feels like the responsible position, the grown-up position, but every year we spend being appropriately, rigorously skeptical of a signal that turns out, decades later, to have been real is a year we didn't spend building the next generation of instruments to confirm it. A year we let the public's attention wander elsewhere. A future Carl Sagan didn't get inspired because we were still busy hedging. Skepticism is a tool, not a virtue in itself. And like any tool, it can be overused until it stops doing useful work and starts just being a habit. So where does the smart money sit right now in the middle of 2026? Patience paired with genuine excitement, which sounds like having it both ways, but bear with me because it's the correct position and not a cop-out. For the first time in the history of our species, we have an instrument, JWST, capable of taking atmospheric spectra precise enough to have these arguments with real data instead of pure speculation. That's not a small thing. Every disagreement about K218b is happening on top of actual measurements, actual photon counts, actual statistical analysis of real light that crossed 120 light years to get here. 20 years ago, this entire conversation would have been pure theory. Now it's an active dispute over real data, which means it's a dispute that can actually be resolved by more data, better data, independent confirmation. That is enormous progress, even though the headline most people remember, alien life found, was premature. The infrastructure underneath the premature headline is not premature. It's the real thing, finally working. Why are we looking at atmospheres rather than just listening for radio signals, the way SETI has since Frank Drake pointed a telescope at two nearby stars in 1960 in what was called Project Ozma? We're doing both. They answered different questions. A radio signal would mean technology, deliberate transmission, something building and operating equipment. A biosignature would mean biology, full stop. Not necessarily anything intelligent, possibly nothing more than microbial life doing the same simple chemistry for 3 billion years, which is exactly what dominates Earth's own history. Drake himself, in 1961, sat down with colleagues at a conference in Greenbank, West Virginia, and wrote out an equation famous enough, you've probably seen it on a t-shirt, a chain of multiplied probabilities. The rate of star formation times the fraction of stars with planets, times the fraction of those that could support life, times the fraction where life actually arises, times the fraction where it becomes intelligent, times the fraction that develops detectable technology, times how long that technology lasts before something ends it. People treat the Drake equation like it's supposed to spit out a number. It was never built to... Every term, when Drake wrote it, was a guess wrapped in a guess, and most still are 6.5 decades later. What it actually does, and this is the beautiful part, is organize our ignorance. It tells you exactly which questions you'd need to answer, and it tells you by simple multiplication that if even one term turns out vanishingly small, if intelligence is fantastically rare, even when life itself is common, the whole product collapses towards zero, no matter how generous you are with every other term. That's a humbling structural fact, and it's exactly why biosignatures and radio signals are different bets on different terms in the same chain. Multicellular life is a recent arrival on Earth. Intelligence rarer still, technology rarer than that. If you had to bet, you'd bet that life elsewhere looks more like slime than civilization, because that's the pattern on the one data point we have. And there's an engineering reason biosignature hunting is the more tractable bet. A biosphere doesn't have to decide to broadcast, point the transmitter our way, choose our frequency during the narrow overlap when both sides are technologically capable of the conversation. It just has to keep breathing, metabolizing, leaving its chemical exhaust in the air, and if we're patient enough, the light eventually carries that exhaust to us, whether anyone over there ever thinks about us at all. That's not pessimism. Microbial life on another world would be one of the most significant discoveries in our history, intelligence or not. It would tell us the chemistry that got started on Earth roughly 4 billion years ago, and we still don't fully understand how isn't a freak singular accident, but something the universe does reliably. That reframes the question from are we alone into how common is the thing we are. And here's where this connects to something genuinely vast. This entire search is, underneath the chemistry, a search about information. A biosignature is a pattern exceedingly improbable to arise from blind thermodynamics alone, sustained against the universe's relentless pull toward disorder, toward equilibrium, toward the boring, well-mixed, reacted-out state entropy, always wants to push a system toward Life, wherever it exists, is a local, temporary, energetically expensive rebellion against that tendency. Erwin Schrödinger saw this in 1944 in a slim book called What is Life that influenced an entire generation of physicists who went on to help found molecular biology. A living organism survives, Schrödinger argued, by continuously capturing energy and using it to maintain a highly ordered internal structure that would otherwise degrade toward randomness, the way an ice cube melts, the way coffee cools to room temperature, the way every closed system trends toward thermal equilibrium given enough time. Life doesn't break the second law of thermodynamics. Nothing can. What it does is export this order outward, dump waste heat and waste chemistry into its surroundings, and use that exported disorder to purchase a local pocket of order for itself, a structured, improbable arrangement of matter that persists for a while before eventually losing the fight, as every living thing eventually does. A planet's atmosphere held in improbable chemical disequilibrium for hundreds of millions of years is that same signature, scaled up to a planetary level and stretched across geological time, evidence that something, somewhere on that world, has been winning a local battle against entropy for a very long time, continuously, without ever fully letting up. That's, at bottom, the same kind of question physicists ask about what a black hole's entropy is counting, or what it means for information to survive or vanish past an event horizon, different costumes, same bone-deep question about how improbable organized patterns persist against the universe that mostly wants everything to flatten into sameness. I don't say that to be poetic. It's a real working idea in how physicists and astrobiologists increasingly think about what life even is as a physical phenomenon, a vigorous, ongoing argument against entropy conducted with chemistry instead of words. One more concrete picture before I close. The planets we study best right now tend to orbit small, dim, red dwarf stars because the contrast problem is less brutal there. A smaller, cooler star means the planet's silhouette blocks proportionally more light. That's why K2-18b around a red dwarf is even on the table, while a true Earth twin around a sun-like star remains largely out of reach for this kind of study. But red dwarfs are also notorious for violent flares, sudden bursts of ultraviolet and X-ray radiation that drive exactly the abiotic photochemistry that manufactures misleading oxygen with no biology involved. The very stars that make the planet easiest to see are also the stars most likely to be actively generating false alarms. That's not a flaw in the method. It's the method handing you a discount on visibility and quietly charging you extra in uncertainty. Closing that gap, getting good spectra of true Earth analogs around sun-like stars, is one of the explicit goals driving the next generation of space telescopes, and it's one of the most exciting engineering pushes in all of astrophysics because it's engineering in service of maybe the biggest question our species has ever asked. I want to leave you with the part that isn't solved. We don't have a complete, agreed-upon framework for assigning confidence to a biosignature claim, the way particle physics has. Its 5 sigma standard for declaring a new particle discovered a standard that exists because physicists got burned often enough by statistical flukes that the field collectively agreed on a brutally strict threshold before anyone uses the word discovery. Astrobiology has no equivalent number, no equivalent culture of agreement, not yet. The field is actively trying to build one framework, attempting to formalize how many independent lines of evidence, ruling out how many abiotic alternatives should be required before candidate becomes detection. That framework doesn't exist yet in a form the whole field has settled on, which means right now there's no universally agreed answer to how sure would we have to be before we'd all say it out loud. That should bother you. It bothers me. because the line between exciting